Okay, so welcome to 4Keys Private Tuition. So we're going to look at rate graphs in this video. So rate concentration graphs can be used to identify the order of a reaction, rate versus concentration. It's important to know that the first graph that we looked at is a concentration versus time. So concentration of a reactant versus time. We said you can look at change in concentration of a reactant or product versus time. That was the first thing we discussed. But here we are talking about rate versus concentration. And how do you determine rate? You need to remember that rate is found by taking the gradient at various points on the concentration time graph. So the same concentration time graph can be used to determine rate. We saw this, that our rate is equal to the gradient. So you can look at gradient at various points and you can plot that data against the concentration of the particular reactant in question. So for example, I can tell you that this is my concentration time graph, concentration versus time, and I can see that my concentration is decreasing over time, but I can see here that the gradient seems to be constant, so there's no change in terms of rate. The gradient is not really changing here. So if I were to plot my rate versus concentration, I would get a straight line like this. It tells me that the reaction is zero order with respect to A. If I plot my concentration time graph and I get a curve like this, I determine the gradients which correspond to rate at different points here, and I plot that data. This would be the gradient rate that I'm getting from this, but I plot it against the concentration data that I have, and I get a straight line going up like that. I know that it's first order. And then so we're just looking at the shape here to determine order. And if I get a steep curve here which translates into a curved line like that for the rate concentration graph, then I know that this is a second order with respect to A. So you can just look at the shape, but this is not reliable. So what you would want to do is to use half-life. Okay, so what is half-life? Half-life is the time it takes for half of the reactant to be used up. So it is the time it takes to use half of the reactant, or to half the concentration, the initial concentration of a reactant. So how do you use half-life? So half-life can be calculated using a concentration time graph. So if I have my concentration time graph, the one that I started off with, then I can determine the half-life here. So what I have to do is check here. I have an initial concentration here, and I can see how long it takes to halve that concentration here by looking at the time here. So from here to here, so that would be 200 here seconds, and I can continue from here. How long does it take to halve this concentration? So I can follow this through and continue to see whether my half-life is constant or not. Okay, so this is how you would determine half-life from a graph. So according to this, it takes 200 seconds for half the concentration to decompose. Okay, so we can pick any concentration value, as I said, and follow through to see whether we are going to get the same half-life. From this graph, we can see that the decomposition of hydrogen peroxide takes 200 seconds to halve its concentration, so the half-life remains constant. So as you continue to halve this concentration and checking the time, you see that the half-life is the same, 200 seconds. But this is not always the case. In other situations, my half-life can also change. So we can also calculate the rate constant K from half-life. The equation is this, so you can determine the rate constant from half-life. So 0.693, a constant here, divided by half-life. For example, here 0.693 divided by 200, and our K is this. So this is important to be able to determine K from half-life. Okay, let's move on. So we talked about this. The concentration time graphs can help us to identify the order, but in this case, what we are doing now is we are looking at the actual half-lives. So it's not just about the shape, but it's now about something measurable, which is our half-life. So let's look at this one. So for a zero order, the rate on a straight line graph is constant. Changing the concentration doesn't change the rate. Then our half-life decreases. So you can see that if you were to determine half-life here, this is the concentration to here, the half of this initial concentration. You can tell that your time here, initially the time is large here, but as you continue to assess your half-lives, you see that the time starts to decrease, or the half-life starts to decrease. So when half-life progressively decreases, it tells us that it's zero order. Now if you have a concentration time graph and your half-life, you assess half-life using this graph, and you see that your half-life remains constant as we saw in the previous example, then this tells us that the reaction is first order with respect to that particular reagent that you're looking at. So changing concentration, changing the rate equally, and our half-life is constant. So we are now measuring half-lives. We are not just looking at the shape, we are looking at actual half-lives to determine the order. So let's look at the last scenario. So for a second order, this is particularly important for these two types of graphs. So how would you just look at this shape and say this is first order, this is second order? So you can't really do that. You need something measurable. You can't just rely on looking at the shape. So particularly for this first order and second order, you would need these graphs. For this type of graph, it may be very obvious that it's zero order, but for these two, to make a distinction, you actually need to measure half-life. So the rate on a steep curve graph changes in unequal amounts, changing concentration, changing the rate, and half-life increases. So for this one, you're going to see your half-life increasing. We said here it decreases, here it's constant, but this one, the half-life is going to actually increase over time. So you have to come and assess for half-life and see whether it's increasing. If it's increasing over time, then you know that it's second order with respect to that particular reagent. So this is how you can use concentration time graphs to identify the order of a reaction. So in the next video, we're going to look at what's called the rate determining step, which is okay, let's just preempt it here. The rate determining step is the slowest step in a multi-step reaction. So certain reactions happen in a series of steps. They don't just happen in one step, but probably 2 steps, 3 steps. And most of them are going to be 2-step reactions. We'll go to organic chemistry where you can have several steps. So of those steps, the slowest step is called the rate determining step. So the rate of the reaction is going to be determined by this step, and whatever is participating in this step is going to appear in your rate equation. Everything else is outside our rate equation, because everything that's participating in the other steps, in the faster steps, is not affecting your rate or your speed. So whatever is participating at this important and crucial step is what's going to appear in your rate equation. Okay, so you need to know this. So this is just an example. When you want to cook a cake, you're going to do it in a series of steps. So this is the same thing with the reactions. They can take several steps. Okay, so continue and proceed with this in the next video. So I will meet you in the next lesson. If you have any questions, you can forward them to me so that we continue with this material.